Late last year, a processor colder than deep space spent about 2 hours measuring a single number. The fastest supercomputer on Earth would need roughly 3 years to compute that same number. And unlike every quantum computing record before it, this one comes with a way to check the answer. The machine is Willow, Google Quantum AI's superconducting chip, and the algorithm has a memorable name: quantum echoes. It works the way a bat maps a cave. You send a signal into a system you cannot see inside, let it bounce around, and learn about the interior from what comes back. Except here, the cave is a chaotic quantum system of over 100 qubits, and the echo is engineered by running time forward and then backward. Here is the whole trick. The chip runs a long sequence of quantum gates forward, letting information scramble across the qubits like cream stirring into coffee. Then it nudges exactly 1 qubit, a tiny, deliberate butterfly flip. Then it runs the entire gate sequence again in reverse. If nothing had been touched, the system would return to where it started. But that 1 flipped qubit has spread its influence everywhere. And when the reversed evolution comes home, the disturbance interferes with the original, and out comes an echo that carries information about how every part of the system talks to every other part. The team published the result in Nature in October, and the measured quantity has a technical name: an out-of-time order correlator. Physicists have wanted to measure these for years because they track how fast chaos spreads through a quantum system. The problem was always noise. The signal is faint, and in a large system, it normally drowns. This is where the paper's title phrase, constructive interference, earns its place. A quantum system explores an astronomical number of paths at once, and most of them cancel each other out. Google's team found that in the second-order version of this echo experiment, huge families of paths line up and reinforce instead. All those faint contributions stack into one signal strong enough to measure, even at long times, when ordinary measurements have already faded into static. That same interference is exactly what makes the number brutal for classical computers. To predict the echo, a simulation has to track all of those interfering paths at once. Google's benchmark used 65 qubits, and the team estimates that computing 1 data point to the same accuracy on Frontier, one of the world's fastest supercomputers, would take around 3.2 years. Willow collected the measurement in about 2 hours. That is roughly a 13,000-fold gap. Big speed claims have come out of this field before, and some of them aged badly. In 2019, Google's Sycamore chip performed a sampling task supposedly out of classical reach, and within a few years, improved classical algorithms had closed much of that gap. The catch was that sampling produces random outputs. There was no single answer anyone could double-check. Quantum echoes is different in one specific way. The output is a physical quantity with a definite value. Run it again, and you should get the same number. Run it on a different, comparable quantum computer, and you should get the same number. Google went at its own claim hard, testing it against 9 different classical simulation strategies before publishing. And in the months since, outside researchers have thrown some of the strongest known classical techniques at it, including the tensor network methods that undermined earlier records. So far, the gap has held. That is still a claim about today's algorithms, and classical methods keep improving. But peer reviewers who called for caution on past announcements have described this one as genuinely impressive. So what is a checkable echo actually good for? This is where the story stops being about racing supercomputers. Because another quantum system that can run the same echo experiment already exists: nature itself. Molecules are quantum systems, and chemists have been bouncing signals off them for decades using nuclear magnetic resonance, the same physics behind MRI machines. If a quantum chip can simulate a molecule's echoes,
you can compare the simulation against the real thing and tune the simulation until the echoes match. Whatever structure the simulation ends up with tells you the structure of the real molecule.
Google tested this idea with chemists at UC Berkeley. They took real echo data from 2 small organic molecules, including toluene, and used Willow to model the molecular echoes and pull out structural details, like a ruler that can measure distances between atoms farther apart than standard analysis handles well. Then they checked the predictions against a real spectrometer. They matched. To be clear about the size of this step, those molecules are small, and a classical computer could still have done this particular analysis. The demonstration shows the loop works end-to-end on real molecules with today's hardware.
Scale that loop up, and you get the actual prize. The shape of a molecule decides how a drug binds, how a battery electrolyte behaves, how a catalyst grips its target. Today, when molecules get complicated, chemists lean on approximations that blur exactly the details they need. A trusted quantum echo simulation could act as a second instrument, sitting next to the spectrometer, filling in what the approximations lose. Google's team is optimistic enough to put a number on it. Real applications within 5 years. That is a bet. And the hard part? Doing this for molecules too complex for any classical method at useful accuracy is still ahead.
For 30 years, quantum computing has promised that one day it would tell us something true about the world that nothing else could, and asked us to take its progress reports on faith. This result is the first one that hands over a number and says, "Go check." The echo came back. The question now is what to point it at.